Hello, John.
Hey, Bob.
How you doing?
I'm doing pretty good. How about you?
I never complain on my show about how I'm doing. So there's almost no point in asking me. You're not going to hear anything bad from me. I save that for my family.
Good for you. Okay. There is this one weird thing that just happened to me.
Okay.
I'm not going to complain. I'm just going to point it out because it was unusual. So
you're not going to judge it. You're not going to judge this thing. You're making no judgments. It's not neither good nor bad, but you're going to tell us what it is. Okay.
It's just a weird thing that happened to me. And it actually was kind of a glitch in my summer plans when I wanted to be writing this book on quantum mechanics.
But let me interject. That's what we're going to be talking about is quantum physics. And I'm looking forward to this because at the moment, I don't understand quantum physics, and you have assured me that by the end of a conversation with you, I will fully understand it because you've really been looking into it, and that's just great. I'm feeling good about that. Now, go ahead.
All will be disclosed.
Yeah.
All right. So I hurt my this elbow, playing hockey in January. I banged it hard, and then I banged it again about a month later. I don't wear elbow pads because I never fall down. That's what I thought. But then I fell down and repeatedly, actually, banged the hell out of my elbow and it swelled up and it got infected and I was putting off surgery and it became septic and I was feverish and hallucinating.
Oh my God.
And checked myself into a hospital, in late May, actually Memorial Day weekend, and I had surgery, and that's what it looks like now.
You didn't have to show us the scar, but thanks.
It used to have these really amazing metal staples all the way down, about 40 of them. Those were taken out a couple weeks ago.
Oh, I wish we had taped then. That would have been some dynamite video. So what did you hallucinate? Did you?
I don't know if you've ever been really feverish.
When I was a little kid, I used to get delirious when I got fevers a couple of times. There was a spooky thing that I remember that I would think. But go ahead.
For me, it wasn't anything specific. It was more that everything was off kilter, and I had a lot of anxiety. Some of this was I was trying to go to sleep, and I was kind of going in and out of sleep, and when I was awake or sort of awake, everything was just really strange and ugly and scary.
But you weren't imagining, like when I was a kid, one of my two feverish kinds of hallucinations was that ants were crawling all over me. You didn't get to that level of, that's really, no. Avoid that one. I recommend avoiding that one.
Thank God I did not have anything that dramatic. But, so anyway, sepsis is serious. I could have had my arm chopped off. And, thank God for antibiotics.
That would have been some video, but so, well, I'm glad you're with us. I mean, by way of transition, under the many worlds interpretation of quantum physics, there's a version of you that it did not hurt his elbow.
Or that died of sepsis.
Yeah, there's one of those too.
Or that had to have his arm chopped off. Or, yeah, you're right. There's a version in an ideal universe where I'm intelligent enough to wear elbow pads, which all my teammates had been bugging me to wear for years. Next season, of course, I will be wearing elbow pads.
Yeah. Okay. Well, good. So let me say a little bit about your impressive credentials. You're one of the deans of American science writing. That would be a good term for you. You've written for a long time for Scientific American. You wrote a famous book called The End of Science. And aside from that, what are your two or three most plug-worthy books? You don't want to forget your recent bid to become known as the second James Joyce.
Right. So, I mean, I love all my books. I've always wanted to do something fictional, so I wrote a kind of fictionalized version of a day in my life recently called Pay Attention. People can find that on Amazon. That came out like last Christmas. And before that, I wrote a book called Mind-Body Problems. I'm obsessed with consciousness and how matter makes mind, which is related to quantum mechanics. And so I wrote a book called Mind-Body Problems. I posted that online. People can read it for free.
Okay.
So I also wrote a book about mysticism,
Rational Mysticism.
Yeah.
Is the title. Did you know that there was a book long ago called Rational Mysticism? Did I tell you that? I came upon it in the Princeton Library about 12 years ago. It was published 60, 70 years ago. Same title. I forget what it's about. Probably Rational Mysticism. So here's, what is this deal like? So you declared some time ago that you were going to get to the bottom of this quantum physics thing if it was the last thing you did. And you didn't put it quite like that, but you said you're really going to try to understand it more clearly. Really, you're even learned math and stuff, which, by the way, I'm not sure I would have recommended for reasons I could get to. But what is the deal? Are you going to write a book about this or what?
Yes, I am. So what happened was I had all these plans for summer 2020. I was going to go to Namibia, a country in Africa, with one of my best friends, a guy named Robert, and my son Mac. We were going to have this great adventure. That was canceled. I had this other, fellowship I was hoping to take. And so it was May 2020, and I'm trying to figure out what to do with myself. I have all this summer vacation because I'm a professor. And I saw a video by this kind of frenemy of mine, Sabine Hassenfelder. It's this really cool theoretical physicist.
Yeah, I've had her on the show.
She's great, really strong opinions. And she's posted all these videos. She's become sort of an internet sensation for these videos on physics and mathematics and all these related topics. So in this video, she said she was going to explain the difference between superposition and entanglement, and in really simple terms. So I thought, hey, great.
Should we briefly say that these are two of the weird, and I don't even know if they're closely related, things about quantum physics?
They are closely related. Superposition, briefly, is just the idea that, the quantum formulas describe a range of possibilities which are said to be in superposition with each other. Each possibility is described mathematically, and they're all kind of summed up. And entanglement is actually a special kind of superposition that involves more than one thing that are in states of superposition at the same time. So it's complicated, and these are principles that are fundamental to the famous quantum weirdness. So as I said, I've written about quantum mechanics for decades. I've written big, long articles for Scientific American on quantum mechanics without ever knowing really what the hell it's about.
And can I just say one thing about I might as well get this point out about why bother to learn the math. And this is the point. So superposition, the idea is, first of all, the math of quantum physics is in certain circumstances predictive only in a probabilistic sense. Mm-hmm. We can say that if you say, well, where are these electrons, or what spin do they have, or something about what property they do electrons even have spin? Who knows? There's some property. There's some property that you're going to measure, and the most the math can do is tell you what percentage of the electrons are going to turn out to have a certain measurement. Or they can tell you, if you keep doing the thing over with a single electron, what percentage of times it will, say, be found here, or have a certain velocity, whatever the measurement is. But the math can't tell you in any given instance what it's going to be. And the weird thing is that, according to quantum physicists, that's not just because that we don't know enough. It's reflecting, well, some of them would say, it's reflecting something about reality, and the superposition refers to the way they conceive of where the particle is before they measure it.
Yeah.
And it's like, it's in some sense, well, one interpretation would be, it's in all these places. It has all these velocities, and then the act of measurement forces it to assume one specific one or something. Anyway, I've given people a sense for what
right.
superposition is. I hope, but as for the math thing, so like I take them at their word, like the math is predictive only in a probabilistic sense, and they are, and it's like, I don't know why, I would not have bothered to learn enough math to confirm that claim. I trust them. like, okay, it's only predictive in a probabilistic sense. Now, what I want to understand is why you're telling me that doesn't just reflect our lack of knowledge about the system at an earlier point or something, why it really reflects something weird about the universe. You see my point?
Absolutely. We have to get to that, because that is fundamental.
Okay,
to
so
the whole
we can
attempt
bracket that, and you can get back to your story about how this happened.
So I'm watching this video. It's like a 10-minute video by Sabina Hassenfelder, and I'm like, and she's explaining the terms, and then she says, there's a little bit of really simple math underlying these principles, and so then she gives the math and introduces some technical terms, and then she lost me, right? And this is an experience that I've had over and over again as a science writer writing about physics, that you get into the realm of mathematical explanations and technical explanations that are based on the math, and that's a world I can't enter. I'm on the outside. I'm relying on the experts to explain what's going on and what the math means, but I just have to take it on faith. And the thing is, I've never taken physicists at their word. I'm second guessing them all the time.
Yeah, I've noticed that about you. Second guessing is kind of putting it mildly. What you're doing all the time to almost all scientists is saying, I think you're totally full of shit.
I try to introduce doubt into discussions about
okay, that's a better way to put it.
Scientific claims, and so seeing this video and this very familiar feeling of frustration that I've had over trying to understand physics and then hitting this wall eventually, it just made something click in my head, and I thought, I'm going to do something about it. I'm going to try to understand quantum mechanics with the mathematics, the way that physicists understand it. Mm-hmm. And the real catalyst, the reason why this became a serious project, I've been doing it for more than a year now. And it's absorbed a lot of my time and energy, is that I got this idea for a book. I'm going to write about an old guy who, was an English major and then became a science writer, but never understood any of the mathematical models, about him trying to learn the math. And
you mean a nonfiction book that's a first-person book about yourself?
Yes.
Okay.
Yeah, it's going to be, it's not
that you're old, but go ahead.
It's not so much a book about quantum mechanics. It's about a guy trying to learn quantum mechanics at an advanced age. And so I thought, yeah, it's going to be really cool. And then I thought, okay, I've got to run this by my girlfriend. My girlfriend, as you know, is...
Can I just say, I know her, and she's kind of a harsh judge. If I were you, I would sometimes seek a second opinion, okay?
Well, I have to run it by her at some point because she's going to hear a lot about it. If I'm working on a book, I'm yammering all the time about it. And so I got this idea. I started getting really excited. And then I thought, okay, I've got to run it by Valerie. And so I was at her apartment. I was in the living room. I went into the bedroom. She was lying on a bed reading. And I said, Valerie, I think I know what my next book is about. So I described this idea. I'm going to try to learn quantum mechanics. I'm going to write about that experience of trying to understand what in some ways is the hardest scientific theory to understand, but it's also crucial for our modern worldview. And Valerie, most of my ideas, she goes, "Oh my God, John, that is so stupid. No, please don't do that. Nobody's going to want to read a book like that." Some of the books I end up writing them anyway, and she turns out to be right usually. In this case, she goes, "Hey, that actually sounds kind of interesting." She said the genre of old guys who were sort of sensing their mortality and try to do something to sort of, keep death at bay, that genre often does quite well. So I was like, yes, all systems go. Let's go ahead and do this thing. And and the first thing I did was I thought, how am I going to do it? What am I going to read? What do I really need to know to say I know quantum mechanics like a physicist? So I know all these physicists and philosophers of physics. So I started writing some of the people I know, including Sabina Hasselfelder. And I said, I've got this idea. And, what should I read? How should I go about this? And I started getting all these suggestions and, like a reading list. One of the first books, a couple of them suggested that I read. It's this book by Leonard Susskind.
Yeah.
It's a bestseller. It's kind of like what you need to know to really understand quantum mechanics.
It's called Quantum Mechanics.
It's called Quantum Mechanics, but the subtitle is crucial. It's called The Theoretical Minimum. So he's saying this is kind of like a bare bones presentation of quantum mechanics with the mathematics that will allow you to say, quantum mechanics.
Did you read any Richard Feynman? There's part of his book, The Character of Physical Law.
Here it is. While I was waiting
QED. Well, that's his big tome on quantum electrodynamics.
While I was waiting for the Susskind book to arrive, I read this and then I reread it because it's actually a pretty difficult book. Technically, it has no math, but it has a lot of diagrams and, it gets.
That's what he won his Nobel Prize for, basically, developing quantum electrodynamics.
I just want to point out an irony and Suskind's, and people recommending Suskind's book. So Leonard Susskind is this big shot physicist at Stanford, and we had a kind of exchange back in 2005. I wrote an op-ed for the New York Times, called In Defense of Common Sense. It was a criticism of scientists who sort of fetishized theories that violated common sense. And quantum mechanics is kind of the epitome of that. And while I was writing this thing, I bashed multiverse theories and string theories. And Leonard Susskind is a major proponent of both those things. And so on this website called The Edge, where, a bunch of people hang out, Susskind said, basically, John Horgan is an ignoramus. He doesn't know what the hell he's talking about. Instead of yammering about all these things that he doesn't understand, he should learn some real physics. He should take some courses in calculus and linear algebra and quantum mechanics and all these other things. And at the time I said, basically, fuck you. I'm not going to do that. That's not my job as a science journalist. But it stung me. And so, here I was all these years later reading his book and kind of taking his advice on trying to learn. And has
learning the math helped at all?
The answer to that is complicated. Let me just tell you that over the summer, I started reading this book and I'd been assured that he teaches you the math you need to know.
This is the Susskind book.
Yeah, this is the Susskind book. He teaches you the math as he's going. And that's bullshit. Total bullshit. I quickly realized I needed trigonometry, which I actually took in 1968,
right.
and logarithms. I'd totally forgotten, what's trigonometry? What are sines and cosines and tangents and all that stuff? What are logarithms? What's the difference between logarithm space 10 and natural? I didn't remember any of that stuff. And then calculus, I actually took calculus when I was finally finishing school back in 1980. I didn't remember anything. Yeah, I was finishing college. I didn't remember anything about, derivatives and so I'll show you some other books I read.
That's all I remember, the word derivative. Quick calculus, okay.
I read that. And then
linear algebra.
Linear algebra.
Man, this is crazy. You better write a book after all this, man.
What was so cool was that I actually loved math when I was a little kid. And I still love it because, there are math problems that actually have solutions. And, unlike so many of the problems that you and I
why is there something rather than nothing? Yeah.
Why, or, like, what should we do about Israel and Palestine? Or
what should I have for lunch? Yeah.
What should I
the whole spectrum.
Yes. I mean, the realm of the humanities, and I'd say most of human life, consists of problems that do not have uniquely true answers. But in mathematics, there are those sorts of answers. And so I actually enjoyed, because it was also really grueling and tedious, learning the math. I didn't learn nearly enough math to really understand, for example, Schrodinger's equation. That requires something called it's a partial differential equation, and it requires more calculus than I was really capable of learning.
Now that is an example of an equation that makes one of these probabilistic predictions I was talking about.
Except,
yeah.
So as soon as you make a statement like that, you are, you're saying something that a lot of people are going to disagree with. Mm-hmm. So the whole question about whether quantum mechanics is really probabilistic or deterministic is up for grabs. So, for example, you've heard of the many worlds interpretation. The many worlds interpretation is an attempt to take the probability out of quantum mechanics by saying that all the possibilities represented by the Schrodinger equation, and there are other ways of representing quantum stuff as well. That's what linear algebra is. This is matrices, vectors in Hilbert space and all this kind of stuff. Many worlds attempts to make it all deterministic by saying that all the possibilities are realized in all these branching universes.
And this is a theory where literally, if you take this seriously, there is or could be a John Horgan who didn't hurt his elbow and one who did hurt his elbow. I mean, literally, they're saying the worlds are like always branching off into these different realities. So there's just this countless different number of realities in which there are different versions of you. And there are smart people who take this seriously. But anyway, go ahead.
Yeah. So you're talking about, why do you need to know the math? What does the math tell you? I've learned enough math so far to realize how much physicists fetishize and reify the mathematics. They reify something like Schrodinger's equation. I tried to talk about this in a column for Scientific American with the title, "Is the Schrodinger Equation True?" So somebody like Sean Carroll, for example, very prominent physicist and physics writer, I would say he fetishizes the Schrodinger equation. He thinks that it is like an expression of some kind of ultimate Platonic reality, and that's what leads him to think that the many worlds theory must be true, because the Schrodinger equation explains the whole multiverse. Actually, last fall, this is part of my, this adventure that I've been on. Last fall, I took a real course, like a graduate level course in quantum mechanics at my own school, Stevens Institute.
Wow.
PEP 553. It was like a punch in the face. Like the first day, I was so far in over my head. I mean,
and was that because you still didn't have enough math?
Not
or
even
you didn't
close.
have enough physics, or you also didn't have enough
Nothing.
preparatory physics, probably.
I didn't have enough of either of those things. Like most of the other students had already had like 6 or 7 solid years behind them of all these different mathematical courses, calculus and linear algebra and all this other stuff, probability theory, plus, classical mechanics and quantum mechanics.
Well, did you go up to the professor and say, look, I'm just doing this to write a book? Like when George Plimpton played quarterback for the Detroit Lions so he could write the book Paper Lion?
Exactly.
Exactly.
Yes.
You're just like, you realize this is a stunt, okay?
Yes. Except so the professor is a guy I know. He's a really nice guy. His name is Ed Whitaker. I've known him since I arrived at Stevens because he was interested in my views on physics, and we'd had a lot of discussions about it. And he loved the idea of it and said he was going to help me out. Some of it might be tough, but he'd give me a little extra help. And but then, right away, I was originally hoping to do all the homework and take the exams and to try to get a passing grade. I thought that would be, sort of a good thing for the book to prove that I was progressing. Like in the first week, I realized that was ridiculous.
That's a good thing for the book too, though.
Yeah, it was, and it set up this other thing that happened later on that I hope to get to. But still, the course taught me a lot. And one of the things that I learned, by the way, they're vacuuming right outside my apartment. I don't know if you can hear that or not.
A little bit, but it's not a big impediment.
Yeah.
I mean, we don't understand quantum physics anyway. There's really no point in understanding whatever the hell you're saying about it.
So here's one of the things that, I was so kind of desperate for any sense that I knew what was going on. I just got be constantly grasping at straws. And so we got, I was reading, actually I didn't, where is this thing? For this course, I was reading an honest to God physics text on quantum mechanics.
God forbid.
And, like from the first page, it was like I said, it felt like a punch in the face. And like, you think you can do this, you idiot. Yeah. Think again. Bam. But then there are little moments of illumination. One was, as a kind of passing reference in the book, it described how the Schrödinger equation models the hydrogen atom, really well. And it describes how, the Schrödinger equation helps you understand some of the behavior of a hydrogen atom. But the basic Schrödinger equation does not describe a helium atom, which is the next simplest thing in the physical world, because the helium atom has 2 protons and 2 electrons.
And that's just too complicated for the equation?
Yeah, so hydrogen atom it's got the nucleus, and it's got actually I've mangled this a little bit. The hydrogen atom has the nucleus and it has the electron. That's called a 2-body system. Mm-hmm. A helium atom has the nucleus and 2 electrons. That's a 3-body system. Now, you might have heard of the 3-body problem in physics.
I've heard the phrase.
It's ubiquitous. It applies in classical physics as well. So Newton's equations describing gravity can describe 2 systems, 2 masses that are orbiting each other exactly, but you have to do approximations and use tricks.
Well, what about Einstein's version of what about
it's called the n-body problem. That's the generalization of the 3-body problem. That's a huge problem with general relativity. So when I saw this reference to the helium atom being too hard for the Schrödinger equation to solve, let alone, reality, I thought, hell, man, that's like, and that all these tricks are required, to make the equations work. I thought, then why do people, fetishize and reify the Schrödinger equation? The Schrödinger equation describes very little. You have to add all this stuff to make it match predictions.
You know, can I interject something about Schrödinger that I learned last night while listening to Walter Isaacson's biography of Einstein? I mean, first of all, let me say, if I were going to do what you're doing, I would do it with relativity. That's the thing, because in theory, you're supposed to be able to understand relativity, I think, and yet I don't. I haven't invested a ton of time, but I think its weirdness is almost underestimated by virtue of all the attention paid to quantum physics. Anyway, and you know, Feynman said, you know, people do it. There are plenty of people who understand relativity. Nobody understands quantum physics. Feynman himself said that. But anyway,
right.
Just three quick things about Schrödinger. Einstein, the famous Schrödinger's cat thought experiment seems to probably have been inspired by Einstein, who in a communication with Schrödinger suggested not the cat thing, but a chemical, like an explosion, like something's going to determine whether something explodes or it doesn't. And he's like, it's got to either explode or not. Like, it can't have both of those can't have happened, right? And that may have led to the Schrödinger's cat thing. The other thing is when Einstein was at the Institute for Advanced Study, he said, hey, why don't we bring Erwin Schrödinger here? He's kind of a big name. And the guy said no, because he was pissed at Einstein. The director, but the third, the more relevant, the less gossipy thing is, Schrödinger was it sounds like he was kind of on Einstein's side in Einstein's skepticism about quantum physics, skepticism of a certain kind. Does that make sense? I don't want to get too far off on this, but.
Yeah, that's what I gather from what I've read about. You know, there are all the creators of quantum mechanics had all these ideas they're batting around. My understanding of the Schrödinger's cat thought experiment is that it was a way of highlighting the weirdness of quantum mechanics, which meant that quantum mechanics could not be the last word when it came to reality.
Well, that was Einstein's word was incomplete, I think, even at the time. Yeah.
Right. But what has happened over the last century, as you know, is that some of these philosophical debates have been resolved with experiments that show that, and this is where entanglement is important, that show that that reality actually doesn't have a definite existence before we make our measurements. So that, the electron is moving through space, and Schrödinger's equation or the matrix or whatever, however you want to represent it, has this range of possibilities. And, common sense would tell us that, well, even if we're not looking at it, it's, the electron is either here, or it's got to spin up, or it's got to spin down. And there have been these experiments that have been able to mathematically distinguish between what is called a realistic picture of the world, which says that, yes, the electron...
Is that word realistic or?
Yeah, realistic.
Realistic, okay.
It's sometimes called, I try to avoid the fussy philosophical words. Another word is ontic, which is related to ontology, so it's what actually exists, as opposed to epistemic, which is what we can know, distinguishing between what actually exists and what we can know. And there have been these experiments. One is related to something called Bell's inequality that you might have heard of. This great physicist, John Bell, who was really interested in the weirdness of quantum mechanics, came up with this way to actually distinguish between a theory that says all these little things moving through space have a definite existence, even if we're not looking at them. Between that idea and the idea that is suggested by quantum mechanics, that no, they actually.
So he came up with an experiment that tests those two theories and you're saying the results come out on the side of no, it's not just that we don't know where the electron is. Yeah. It's nowhere in particular, or it's everywhere, or however you want to think about it. Everywhere along the curve of probability, I mean.
Its existence is actually blurry. Yeah. And one of the things that I understand a little better now than I did, when I was writing about quantum mechanics for Scientific American back in the 1990s, is the mathematics behind Bell's argument. It's actually subtle statistical differences between a model of the world that says things are what they are, even when we're not looking at them, and a model that says, no, things don't have a reality in themselves in between our observations of them.
Well, let me say one thing. If you can, in your book, explain how an experiment could tell us which of those is the case, that would be an accomplishment. Maybe people have clearly, I'm sure they have somewhere, but I'm somebody who pays kind of casual attention to this stuff, and I've always wondered, I don't know how an experiment, it just almost seems impossible in principle that it seems like that's the whole point. Is that right? I mean, is that of quantum physics is that an experiment couldn't settle that, but obviously I'm wrong. You're telling me I'm wrong.
Then you get into, some of the technicalities and subtleties of the argument. There's this issue called non-locality.
That is very much related to the entanglement thing.
Right.
I mean, we should say that in entanglement, so there can be these two particles far, far away and moving away from each other even, but because they have been related in the past, because they interacted in the past or something, had some kind of relationship, if you measure, let's say their spin is an actual property and it will always be complementary. That's just a law of quantum physics or something. So, if you measure that the spin of one is 1, the spin of the other is -1. Is that, let's just say heads and tails. It doesn't matter what the property is. It's like if quantum physics says if this particle, if you measure it in its heads, this one that's however far away is at the same moment tails. Now you might say, well, so what? They're just like twins separated at birth. They had the same property at the beginning. They move away and the properties may change according to some time formula, but they're always in sync. And the quantum physicists say, no, we know that neither particle, this property that we're measuring, did not even exist for either particle until we measured it. So at the moment we measure this particle over here, we are forcing the other particle. The moment we measure heads here, we have just forced, in a certain sense, the other particle far away instantaneously to have the property of tails, right, which sounds like influence moving faster than the speed of light, which is one reason Einstein didn't like it. I mean, Einstein thought up this whole entanglement as a thought experiment, right? He pointed out that, you realize this is a consequence of quantum physics. If it's correct, then these particles, we would have influence moving faster than the speed of light. That's too crazy, right? Well, turned out they followed his lead, did the experiments decades later. No, it is that weird, according to them, right?
Right. So here's one of the sort of subtleties that you have to
anyway, let me just mention. Add, so that's an example of non-locality, right?
Yes. Okay. Yeah, which is closely related but not identical to entanglement.
Okay.
There's one interpretation of quantum mechanics that I think you and I might actually have discussed. It was not originally invented, but it was popularized by David Bohm, who was this kind of tormented character in physics who was obsessed with understanding quantum mechanics. The general idea is that he's saying that particles actually, hold on, let me just disconnect my phone.
Okay. While John is doing that, I will just repeat that I don't understand anything about quantum physics. Okay, he's back.
He's saying that particles do have a definite existence and go on definite trajectories when we're not looking at them, but they exist within this strange field called the pilot wave, which has what are called non-local properties. In other words, what's happening way over here instantaneously affects what's happening at all these other places within the pilot wave. And the problem is there's just no evidence that this actually exists. So it's a very kind of clever theory. One of the reasons I bring this up is that a lot of what physicists or philosophers of physics do is argue for different interpretations of quantum mechanics. They're all bad. They're all bad. One of the people I've talked to recently is this amazing philosopher of physics named Tim Maudlin. I think you talked to him.
I've had him on the show, yeah.
As well. And, he wrote a book in which he's intent on sort of establishing what's really going on. What does quantum mechanics tell us about what's actually happening in the world? And I think his favorite is the pilot wave theory. But Maudlin is so honest in talking about all the interpretations that by the time I was done reading his book, which I have somewhere over here, I thought, they're all bad. Come on, Tim. I mean, all these interpretations, it's just, you're swapping one kind of nonsense for another kind of nonsense. It's the pilot wave versus the unreality of particles moving through space.
But by nonsense, don't you just mean kind of literally, it doesn't make sense to us intuitively. We can't conceive of it. We can't come up with a picture where it makes sense. That doesn't mean it's not in some sense true, right? I mean, this is, of course, the thing about quantum physics. It forces us, and I think relativity, again, does this more than we maybe some people appreciate. It forces us to recognize the possibility that the nature of reality is just inconceivable to us.
So I actually want to make a riff off what you've been saying about relativity is pretty weird too when you think about it. That is another thing that I've learned over the course of this project. There's this distinction between quantum physics and classical physics, everything that happened, before the quantum revolution in the early 20th century. There's a great book.
And relativity is classical, however weird, right?
Yeah. It doesn't have, the indeterminacy of quantum mechanics. This is a book by a friend of mine, George Musser, a really good physics writer. And it's called
Spooky Action at a Distance, which is Einstein's phrase.
Yeah. It's a reference to non-locality, which we were just discussing. How can one thing happening over here instantaneously affect what's happening over here? And George points out in this book that spooky action is an ancient idea. And so Newton's theory of gravitation is a spooky action theory.
Yeah, but Einstein, however weird relativity, seemed to take that part out of it, right?
Well, sort of, because he showed it's related to the to the speed of light. But the
well, no, but what I mean is, he said, like, if two heavenly bodies, you can think of the moon being influenced by the Earth or something, right? But and the Earth is far away, so that's spooky action at a distance. But if what the moon is responding to is the contours of the space-time continuum in its immediate vicinity, right? It's actually responding to the curvature of space-time right where it is, right?
Right.
So that takes the spooky action out. That's what I meant.
Well, so here's the larger point that I want to make, and this is kind of a realization that's been gradually dawning on me over the last year. I don't understand quantum mechanics. I understand it less, I think, now than I did a year ago. The way I sometimes describe it is, it used to be like a total, just an undifferentiated mist. Now when I look into it, I see like blobby shapes in the mist. And, that's about it. But it's still like a total mystery. But what's happened is that everything else in the world, all our other forms of understanding, supposedly, have become more mysterious to me as well.
Like what?
Let me compare ordinary language to mathematics. This is sort of tangentially related to what I'm just talking about. Mathematics is, we're trying to understand linear algebra and differential equations, things like that, and go, oh my God, that's hard. Mathematics is so logical and simple compared to the kinds of communication that's going on between us right now. Ordinary language, the rules of ordinary language are extremely difficult to sort of put down in a clear-cut way. And the vocabulary that we use is just totally ambiguous, and yet we're habituated to language. We're not aware of all these problems, all these complexities with ordinary language. I think what happens in science, too, is that the physicists become habituated to a theory like, first of all, Newton's theory of gravity, which is really weird if you think about it. Things influencing each other across space. And that's replaced by Einstein's
which is weird in its own way, because you can't even conceive in your head of this four-dimensional space-time continuum whose curves the bodies are responding to.
So the physicists become habituated to these theories, and they say, what's the big deal? It makes perfect sense.
Mathematically, it does, yeah.
When actually it's a kind of, I think this is an unfortunate consequence of the way that physics is taught, is that it's kind of a brainwashing process or a form of habituation where you learn all these techniques, these mathematical techniques that are often extremely removed from what's going on in the world. The techniques are intended just to solve problems. And you get further and further away from what would count as ordinary understanding. And for me, this applies to everything, to my understanding of myself, to my understanding of other people. So the deeper I've gotten into this project, the more I've become like hopelessly befuddled by everything. And I think that our sense that we know what's going on in the world comes from just habituation. We're kind of used to it.
I'm not sure this is the happy ending your book needs, John. Old man gets more befuddled. That'll just jump off the shelves.
Well, I'm worried about reaching a foregone conclusion, but this idea of, when you see the world accurately, truly, you should be befuddled. This is something that comes out of, my psychedelic experiences, my fascination with mysticism. The deepest insight of mysticism to me is that the world is completely mysterious. All our knowledge, whether coming from philosophy and humanities or our common sense, whatever you want to call it, as well as our most esoteric physics theories, all our knowledge is completely inadequate to really understanding what's going on in the world.
Yeah. No, I mean, what's amazing when you think about it is that animals that evolved through natural selection have gotten as far as we have. That's completely amazing. That's completely,
yes,
just look at the technology we produce, which of course is based on scientific understanding of the world. It's completely amazing. No, I agree that more amazement, amazement's not a bad ending for a book. So, maybe you should move from befuddlement to amazement, before the book ends. I like
befuddlement. I just like that word.
Yeah, it's a good word. I just think it should be the penultimate chapter, not the ultimate chapter. So here's just to pick up on the all roads lead to befuddlement theme, like we've been saying, there's, there was disagreement that some physicists say is now experimentally settled over whether before you measure the particle, it has definite existence, or whether it doesn't and it only snaps into definite existence when you measure it. Okay, there's that question. But then even if you take them at their word that they've settled it, the question becomes, okay, what is it about the measuring that makes it snap into physical existence? Now, are you saying that a conscious observer is required, like a human being? And I think most physicists would say no. There have been smart physicists who said yes. I think Eugene Wigner maybe said yes. But okay, if not that, then do you mean the physical instrument that measures the particle? And like, if you mean that, how does the particle know the difference between a sophisticated measuring device and any other physical thing it happens to bump into? I mean, are you saying that every time a particle has a physical encounter, it assumes definite? I don't like is there a consensus answer to that question?
So this is a really important issue in quantum mechanics. So, how do we solve the measurement problem, and what about the role of the observer and consciousness and all that? Another book I read recently is by this great British science journalist, Philip Ball, who actually studied quantum mechanics with the math when he was in...
And by the way, there's a conversation between you and him on the Meaning of Life TV podcast feed, I believe, right? The YouTube channel. People can search it on YouTube.
Yeah, I should say that I've talked to a bunch of people about quantum mechanics, George Musser and Tim Maudlin and Philip Ball about all these questions. And Ball wrote a really good book about quantum mechanics, Beyond Weird, sort of saying, listen, quantum mechanics is really not what you think it is. He's going to try to resolve some of the paradoxes. He's got this whole section on what's called decoherence, which is an attempt to get the observer out of the way with the measurement problem. The basic idea is that you get particles taking on a definite existence just when they're being sort of jostled by their environment.
Right. So any physical encounter, in effect.
Yeah. And, there's some technical details there. So basically he's trying to get all that kind of mystical hoodoo out of the way. But then later in his book, and this is something that I talked to him about, on the podcast, later in the book, he says he thinks the correct way to look at quantum mechanics is in the framework of information, and that really what's going on in the world isn't matter moving around in space and forces and energy. We should think of it all in terms of information, and when you do that, then a lot of the paradoxes are resolved, and there are different forms of information theory sort of being fused with quantum mechanics.
I hope you're not going to now tell me we're living in a simulation, John.
No, what the problem I have is that information reintroduces consciousness. The concept of information doesn't make any sense without senders and receivers of something. And the way information was originally defined by Claude Shannon, the inventor of information theory, somebody I actually interviewed about, like more than 30 years ago.
Wow.
Is that he described it as the capacity of a system to surprise you. Mm-hmm. So if you already know something, and then I send you a message and you already knew its content, there's no information. Yeah. So information is dependent on your state of mind, the information you already possess, and the information that you're lacking. And there are connections to physical theory. It's related to entropy, which is a concept in thermodynamics in certain ways. But the crucial thing for me is that information brings consciousness and the observer back into the world. And so you're back with the kind of mysticism that's always been a problem with quantum mechanics. It's part of its appeal also to certain New Age figures. But the fact that information theory is kind of the cutting edge right now, I'd say, in interpretations of quantum mechanics is not a good thing. It suggests to me that quantum mechanics as a whole is really unstable. And by the way, one thing I wanted to sort of confess here, I just passed the 25th anniversary of my book, The End of Science, which came out in 1996. And I had a chapter in it called The End of Physics. And in The End of Science, I was sort of saying that, quantum mechanics and general relativity explain pretty much everything we need to be explained. And it forms this stable system of explanation, and it's just going to last, forever. And now I don't believe that anymore. Quantum mechanics seems unstable. It's right at the foundation of science and of our modern view of the world. And yet it's nuts. And our attempts to understand
wait, but the reply is it's
works.
Not totally nuts because the math works. That part will endure. Even if a new math, if it turns out Einstein was right and there's a hidden variable and a new math comes into being that predicts these things more specifically, non-probabilistically, it will still have been the case that the math was accurate in a probabilistic way, which is better than what we had before, right? Yeah.
So one of the things that's going on here, I think, is that I find really interesting is a kind of schism. What do we want from science? One thing that we want is just understanding. We look at the world and we go, what the hell? And science tries to explain what's going on. Another thing is power over nature. Quantum mechanics is this wonderful case where we get enormous power, but the theory, it makes us more confused about how the world works than we were like 120 years ago. So here's another thing I'm going to talk about in my book that's going to sort of dive right into this dichotomy. One of the people that I heard from last fall when I was writing some columns for Scientific American about my befuddlement was a guy named Terry Rudolph, who wrote this book, Q is for Quantum. He suggested that I read this. And
as authors do.
And it blew my mind. He said, I wrote this book for people like you who are trying to understand the mathematics of quantum mechanics, but you're finding calculus and linear algebra too difficult. And this will teach you what you really need to know. And
it's a really good book.
It's hard. It still was hard for me. I was motivated because I think he said, 9-year-old kids could understand it. And so when I wasn't understanding it, I was going, for God's sake. I mean, if a 9-year-old can understand it, I can understand it. And I actually felt like I understood superposition and entanglement and non-locality and Bell's inequality and the whole debate over realism, versus, non-realism. But here's the sort of...
We should just say realism is the idea that physics tells us something about something that is a reality and it would exist even if we weren't here. And the alternative, which some might call empiricism, I mean, going back to the, empiricist philosophers or something, but it's the idea that, all we know is that the math works, so to speak. And that's all we can ever say.
So here's just a twist related to what we were just talking about power versus understanding. A lot of this book is in the context of trying to understand conventional computing and as compared to quantum computing.
Yeah, I was going to ask about that.
And Terry Rudolph, it turns out, is a founder of one of the leading quantum computer companies. It's already raised hundreds of millions of dollars. And he thinks that they're ahead of the pack. And, of course he would. But I ended up talking to him, and I trust him. And in part because I love his book. And he's convinced me that quantum computing will be a real thing. And another thing that I learned in reading this book is how quantum computing works and what will make it different than conventional computing. It's not just...
That's what I've known, because what I've heard when I've asked is it works in different ways. Different quantum computers work, because like a question I ask is like, wait, does it get its power from the idea that actually, in superposition, there's not just one electron, there's electrons all over the place, and you get each of them to do a little computational work at the same time. I said, like, is that what's going on? And like one person once said yes, but another person once said, no, like, what is going on with quantum computing? I mean, does its success tell us anything about how to interpret quantum physics?
What Rudolph said is that if quantum computing fails, that will be an enormous theoretical advance, because that will tell us that our understanding of quantum mechanics is completely wrong.
What does he mean by our understanding? Does he mean like that interpretation, the kind of superposition interpretation, or what?
Superposition and entanglement. What's going on in computer? So, I mean, just one of the little pieces of understanding that I think I got from his book is that there are calculations that are carried out by particles that are in a superposition that cancel each other out, and something that's similar to interference, where waves cancel each other out. A peak of a wave corresponds to,
if they interact,
the trough of another wave, and they just cancel. And this happens in quantum computing, but only for certain kinds of problems. So there's certain kinds of problems that quantum computing should be fantastic at, but it's not going to be like a magic wand that you can wave over all the problems that science faces, or that we face, just as a social species, with climate change and everything. It's not going to just make all those problems disappear, give us the unique solutions to them. But for some kinds of problems, it can be really powerful. Now, just one other thing I have to mention about Terry Rudolph, and he's a little squeamish about mentioning this himself, but he happens to be the grandson of Erwin Schrödinger.
Really?
This is something that Rudolph was already, I think, in graduate school for physics, and he found out from his mother that Schrödinger was his grandfather. And
whoa! She hadn't mentioned that. I mean, so she was not. He was not actually. Erwin Schrödinger was not married to her mother. In other words,
this is one reason why he doesn't. Anyway, so I'm a writer, and so when I found out that this guy who had written me and had suggested this book that had this kind of pedigree, I thought, well, I've got to mention that. But he himself would rather.
And by the way, this isn't maybe not related, but I only vaguely recall the story. But didn't Schrödinger conceive the equations while having a wild, like I have this idea, he went to like a mountain cabin with some woman and had a wild affair with her or something, and in the course of the ecstasy, he was in such a good mood, and so or something, he conceived of the Schrödinger equations. There is some story like this, and I just want to say, if this guy is a descendant of that relationship, and who knows, maybe that was Schrödinger's wife, but I don't think so. Anyway, then he is truly charmed.
Well, he's a very modest, self-deprecating guy, but as I said, he's the leader of one of the top quantum computing companies.
What's the company?
World. It's called PsiQuantum.
PSI?
PSI, PsiQuantum.
Doesn't PSI refer to like paranormal stuff or not? No?
No, it's actually, I think it's the term for the wave function, which is the funky looking, funky looking trident in Schrodinger's equation.
So anyway, so I'm sorry, I got you off the track of what you were trying to get to with via Terry Rudolph. So the book, I mean, we were asking, so what on quantum computing? So first of all, am I totally off base when I think maybe they're getting the different versions of the electron to do work at the same time? You haven't heard that, like about quantum computing? I
have, but I know that no matter what description you use of what's going on in a quantum system, there are going to be some people who are irritated by it and who say, no, that's not right. Whereas there are other people who say, no, that's fine. I know that some of the quantum computing people do not like the sort of parallel universe model. David Deutsch, who's this brilliant physicist.
He's a many worlds guy.
He's a many worlds guy. He was one of the originators of the whole idea of quantum computing. He thinks that quantum computers, you've got computations that are happening in other universes, and they come back and converge in this universe. So,
wow, it's mind-blowing that that's even a conceivable interpretation of what's going on in the computers. I mean, that's how crazy this shit is.
So you said you don't want your conclusion to be, I'm just like an old guy. I'm more befuddled than ever. I'm also going to try to talk about quantum computing and some of these potential applications of quantum mechanics, which could revolutionize science. This is another way in which I'm beginning to second guess my end of science prediction. Quantum computing really could be there's so much hype and bullshit, but it still could be something really significant in the history of science if some of the things that they hope to do actually can be done by quantum computers. And it might happen with, like modeling quantum systems. So modeling quantum systems in a way that helps us understand what's going on and might even resolve some of these paradoxes that quantum mechanics poses now. One other thing that I say before we have to stop talking here. I mean, you could tell I love this stuff. I'm so excited by it.
We could have a whole other conversation about this, yeah.
But there's, so once I started learning some of the math, I had a sense of the mathematics as being kludgy and ad hoc, this kind of complicated, jury-rigged thing with all these fixes and add-ons and everything. And it's kind of ugly and arbitrary. And it made me think that it's very historically contingent, and that physics could have gone in another direction that would have made more sense. And it reinforces my idea of both the world being arbitrary and our models of the world also being somewhat arbitrary. Now, there's a counter view that comes from this really brilliant guy named Scott Aronson, who's like one of the deepest thinkers about quantum mechanics and quantum computing. He's written this book about quantum computing that's posted online, and he talked about this arbitrariness of quantum mechanics, and he thinks that's a function of how it's taught and the teaching methods related to previous ideas and all the confusion that Bohr and Einstein and others had about it. Aronson says that the core idea of quantum mechanics is something called negative probability, which doesn't make any sense. But he says, and this is related to something called complex numbers. If you can accept this concept that there can be negative probabilities which cancel out with positive probabilities, which is what happens when you're doing quantum calculations. Again, this is related to interference. He said then quantum mechanics becomes not only less kludgy and arbitrary, it becomes beautiful and kind of inevitable. The way he's described it is, he says quantum mechanics actually it's not really science. It's not like a physical theory. He calls it an operating system for reality. And he says that if you were God, you're the creator, you're trying to figure out how to design a really cool universe that would not be predictable, that would have a great capacity for surprise, then you would want an operating system like quantum mechanics, which had this weird kind of probability theory at its core.
Yeah, in a way. I mean, although some people would say, well, what you'd really want is free will, and randomness isn't the same as free will.
Right. I think Aronson would say that this is a system that actually gives you free will.
Well, then I'll have to write his name down. I want to talk to this person.
Oh, Scott Aronson is brilliant. He's kind of like I think he's 40 now, but he's been like, he was a child prodigy, and I still think of him as like a child prodigy. He's really brilliant, a deep thinker, understands the mathematics and the physics really well, and its relationship to computer science and to the possibilities of quantum computing.
Okay, well, we can leave it there. It really sounds like a great book, and man, it sounds like you've done a lot of research. I say befuddlement should not be quite the final chapter. No, actually, it could be. It could be. I'm kind of kidding there. Yeah, you can go with befuddlement. It could be the name of the book, Old and Befuddled. How does that sound? By John Horgan.
My working title is My Quantum Experiment. And then, I'm not sure what the subtitle will be, but My Quantum Experiment.
Yeah. That's good. I would buy that book. So let's talk about this again. And I don't know how conversant you are in relativity, more than me probably. And I want to have a conversation with somebody about that. Maybe you would be that person.
No, I'd have to spend another year on that. I think you could talk to Tim Maudlin or any of the philosophers of physics about that.
Yeah.
I'd love to watch that because I'm not sure what the philosophical stakes are when it comes to relativity.
Well, I don't even understand. I mean, I have not invested much time. I don't even understand the theory, but I'll close with something I learned from this Isaacson biography of Einstein, which is that, when they gave him the Nobel Prize, it was not for relativity. It was something that he had done earlier and was a little more concrete. And they referred in the citation, the Nobel Committee, like in terms of, when they laud the person who won the prize, they referred to relativity. And as Isaacson said, they referred to it almost dismissively as a kind of epistemological theory, like a theory about how we know things. And I realized, that's my hang up with relativity. I see these interesting epistemological thought experiments. Like, how do we know that these two events happen simultaneously? What does it mean to say we know that these two events? I get all that. I don't get, and I haven't explored it, but how you get from that to the theoretical stuff that's just about the physical universe. Take the people out of it, because Einstein at least wound up being a realist. Interestingly, he doesn't seem to have started that way, but he wound up being somebody who thinks that the laws of the universe should not depend on the presence of human beings, right, to observe them.
Yeah.
So I want to, it's not yet clear to me how we get from these cool thought experiments or even from saying, hey, standing still and being subject to gravitation is like being in an elevator out in outer space that's accelerating, or whatever the hell the experiment is. I want to be convinced, I guess, that relativity doesn't wind up raising some of the same perplexing questions about our relationship to reality that quantum physics does.
Well, I think what you need to know is that I don't know. I've interviewed a lot of the greatest physicists of the last 50 years. And, I think every single one said that whatever the final theory of physics is, if you even believe in that concept, it's going to be a quantum theory. And so, the great goal for the last 100 years of Einstein and other physicists was to unify quantum mechanics and general relativity into a single theory. And there's been a lot of work on that. That's what this thing called string theory is about. There are other versions of it. But all the people who are interested in that and trying to work on it say we're still going to be stuck with all the quantum paradoxes.
So they want to quantize gravity, as the phrase goes. And Einstein wanted to have a grand unified theory that I assume didn't involve quantizing gravity.
Yeah. That's what his hope was.
Because relativity is gravity.
Yeah.
Relativity is our current explanation of gravity. And, I think I don't know any more than I've already said, so I'll shut up.
Okay.
And that'll be the last sentence of your book, too. You can use that if you want.
Okay. Yeah, man. Anytime you want to talk again.
This is always fun. Sounds like a great book.
Yeah, I've become obsessed with this stuff.
Okay. So we will see you down the road. Thank you.
All right.
See you around.